For decades, exoplanet science treated oxygen as the strongest fingerprint of life. Find oxygen and life might follow. Find a star and oxygen might appear. That was the logic. Then dark oxygen was discovered. Observations from Earth's deep ocean now indicate that oxygen can be produced without sunlight through a large-scale abiotic process operating in complete darkness. This single finding destabilizes two assumptions at once: how life begins and where it can exist. If dark oxygen is real, habitable worlds may be far more common than expected, and technological civilizations far more constrained. The universe may not be empty. It may be hidden, breathing beneath stone skies. So what is dark oxygen? Where does it come from, and what does it mean? The answers begin 4,000 meters beneath the Pacific Ocean. That place is the Clarion-Clipperton Zone. To understand the magnitude of this anomaly, we must first understand the environment where it was found. We are dropping into the Clarion-Clipperton Zone, a fracture spanning approximately 1.7 million square miles across the Pacific seafloor. This is not merely deep water. This is an alien world located within our own biosphere. As we descend past the 1,000-meter mark, we cross the final threshold of the photic zone. The sun is gone. For the next 3 kilometers of vertical descent, there is only absolute crushing blackness. By the time we hit the abyssal plain at 4,000 meters, the water pressure has climbed to nearly 400 atmospheres. To visualize this, imagine the weight of a fully loaded pickup truck balanced on the tip of your thumb. This is a hydraulic vise that seeks to crush any pocket of air, any weakness in a hull, instantly and without mercy. In this domain, biology operates on a strict energy budget. It is an oligotrophic environment, a scientific term meaning starved of food. Life here usually subsists on marine snow, the decaying organic detritus drifting down from the sunlit world miles above. Because there are no photons, there is no photosynthesis. In the thermodynamic ledger of the deep ocean, oxygen is a currency that is only ever spent, never earned. Every fish, every worm, every microbe breathing down here is consuming oxygen that originated at the surface, carried down by the slow conveyor belt of ocean currents. Therefore, the baseline rule of abyssal oceanography has always been absolute. In a sealed system on the seafloor, oxygen levels must drop. They cannot remain static, and they certainly cannot rise. This was the certainty that Professor Andrew Sweetman took with him in 2013. Sweetman and his team from the Scottish Association for Marine Science were conducting what should have been a routine survey of the seafloor ecosystem. They deployed deep-sea landers, complex robotic laboratories designed to sink to the bottom and perform autonomous experiments. The landers were equipped with benthic chambers. Think of these as high-tech inverted cups that are pressed gently into the sediment, isolating a small patch of seafloor and the water directly above it from the rest of the ocean. Once the chamber seals, it creates a locked room. The sensors inside begin to log the respiration rates of the organisms trapped within. The expectation is a smooth downward slope on the graph. As bacteria and nematodes breathe, the oxygen concentration should steadily decrease until it hits zero. But that is not what the sensors reported. When the data came back from the abyss, it showed something physically impossible. Instead of the expected decline, the oxygen levels inside the isolated chambers had stabilized and then inexplicably begun to climb. The concentration of oxygen wasn't being depleted, it was being replenished. In the pitch black at 400 atmospheres of pressure, something inside that sealed box was generating fresh oxygen. For a scientist, a result that violates the laws of thermodynamics is terrifying. It implies only 2 possibilities. Either you have discovered a new mechanism of nature, or your equipment is broken. Sweetman assumed the latter. The team concluded that their sensors' optical devices, known as optodes, were malfunctioning, perhaps drifting due to the immense pressure or cold. They recalibrated. They sent the landers down again. They swapped sensors. They employed different methodologies. Yet time after time, the glitch returned. The graph refused to go down. For 10 years, this data was treated as an embarrassing anomaly, a ghost in the machine that couldn't be explained, and so was largely ignored. It was an impossibility tucked away in a hard drive. But the sensors were not lying. They were faithfully recording a phenomenon that human science had simply failed to predict. The seafloor was not inert. It was electrochemically active. If biology wasn't responsible, and in the absence of light, it couldn't be then. The driving mechanism had to be something else, something older than the life clinging to it. The answer lay scattered across the mud in the billions, the black potato-sized rocks that the lander had settled upon. If biology cannot explain the breadth of the deep, then we must turn to geology. And what we find is that we have been moving across vast fields of naturally occurring electrochemical structures for millions of years. To the uninitiated eye, the floor of the Clarion-Clipperton Zone looks like a cobblestone street paved by a careless giant. The sediment is carpeted with billions of black knobby lumps ranging in size from golf balls to potatoes. For over a century since they were first dredged up by the HMS Challenger in the 1870s, marine geologists have classified them as polymetallic nodules. They were viewed as mineral curiosities, inert lumps of rock that happened to be rich in manganese, nickel, cobalt, and rare earth elements. But inert was a misdiagnosis. When we stop looking at them as rocks and start looking at them as components of a system, their true nature is revealed. These are not inert stones. They behave like components of a natural electrochemical system, effectively functioning as geobatteries. To understand how a rock becomes a battery, we must look inside. If you were to slice a nodule in half, you wouldn't see a uniform interior. You would see concentric rings like the growth rings of a tree, but formed of alternating metals. Over millions of years, dissolved metals in the seawater manganese oxides and iron oxyhydroxides slowly precipitate out and latch onto a nucleus, such as a shark's tooth or a fragment of shell. This process is excruciatingly slow. These nodules grow at a rate of just a few millimeters every million years. A single nodule the size of a baseball represents a span of time longer than the existence of the human species. But as these layers build up, they do not just accumulate mass, they accumulate potential. The difference in chemical composition between the layers creates an electrochemical gradient. In the presence of salt water, the ultimate electrolyte electrons can migrate between the layers. The nodule becomes a charged capacitor. When Sweetman's team applied probes to the surface of these nodules brought up from the deep, they recorded a voltage on the surface of a single stone as high as 0.95 volts. To put that in perspective, a standard AA battery in your remote control carries 1.5 volts. These rocks, sitting in the eternal dark and cold, are nearly carrying the charge of a manufactured battery. However, this finding presented a physics problem. To generate oxygen from water, you need to perform electrolysis, supplying energy to split water into hydrogen and oxygen. In a high school chemistry lab, this is easy. In the chaotic high-pressure environment of the deep sea, it is thermodynamically expensive. The theoretical minimum voltage required to split seawater is 1.23 volts. In reality, due to resistance and chemical inefficiencies, you need an overpotential, a surge of roughly 1.5 volts or higher, to get the gas bubbles to actually form. A single nodule capping out at 0.95 volts falls short of this threshold. It shouldn't be able to split water. It's like trying to start a car with a dying battery. The potential is there, but the spark isn't strong enough. This is where the system investigator perspective becomes crucial. We cannot look at a single nodule in isolation. We must look at the grid. On the abyssal plane, these nodules do not exist in a vacuum. They lie in dense clusters, sometimes touching, sometimes sitting millimeters apart in the conductive, semi-liquid mud. In this configuration, they are not individual units. They form a spatially extended electrochemical network where local potentials can combine and interact. Just as you stack multiple batteries in a flashlight to increase the voltage, the proximity of billions of electrically charged nodules creates a cluster effect. The dense field creates microenvironments where local electrochemical conditions are sufficient to overcome the overpotential barrier. Different mineral surfaces within the sediment act as localized anodic and cathodic sites. The seawater serves as the electrolyte. The nodules provide the charge. The result is a phenomenon previously thought to be impossible in nature. Seawater electrolysis operating across vast regions, of the abyssal seafloor. Two molecules of water split into four protons, four electrons, and one molecule of oxygen. This equation describes the electrochemical reaction underlying what we call dark oxygen. It is a silent, invisible reaction occurring on the surface of trillions of stones, constantly cracking water molecules apart and releasing oxygen into the deep ocean. It is a form of planetary respiration that requires no lungs, no gills, and no sunlight. The implications of this mechanism are staggering. We had assumed the deep ocean was oxygenated solely by cold currents sinking from the polar regions, a physical ventilation system. Now we know there is also a chemical ventilation system. The Clarion-Clipperton Zone is not just a mineral deposit. It is a continuously operating power plant. It has likely been running for eons, pumping out oxygen, supporting a diverse and specialized ecosystem that we are only just beginning to catalog. We are standing on top of an extraordinarily complex natural system, a system that turns stone and salt water into the breath of life. And the supreme irony is that humanity actually held the key to this discovery in its hands half a century ago. We touched these batteries, we mapped them, and we even brought them to the surface, but we were so blinded by the context of our own geopolitical wars that we missed the scientific revolution staring us in the face. We are about to open the lost chapter of the Cold War, where the CIA unwittingly stumbled upon the lungs of the deep, but saw only a cover story for a spy novel. The year is 1974. The location is the middle of the North Pacific over a region of the North Pacific Abyssal Plain. A different location, but the same geological environment we are studying today. A massive, peculiar ship named the Hughes Glomar Explorer holds station. To the public and the press, this vessel belongs to eccentric billionaire Howard Hughes, and its mission is the first industrial-scale attempt to mine manganese nodules from the ocean floor. The story was perfect. Hughes was known for his reclusive madness and grand technological ambitions. It made sense that he would build a giant claw to rake diamonds from the deep. But as history later revealed, the mining was a lie. The Glomar Explorer was a CIA asset built for Project Azorian. Its true target was not rocks, but the wreckage of K-129, a Soviet submarine carrying nuclear ballistic missiles that had sunk 6 years prior. The polymetallic nodules were merely the cover story, a boring geological alibi designed to explain why a massive American ship was loitering in the middle of nowhere for months. Here lies the supreme irony of the 20th century. The CIA chose the manganese nodules as their cover because they seemed valuable enough to justify the cost, yet dull enough to avoid deeper scrutiny. They treated these stones as static props in a spy drama. When they dredged up tons of these nodules to maintain the charade, they saw them only as mineral clumps, potential sources of nickel and cobalt for steel production. They held the batteries of the deep in their hands. They likely walked past piles of them on the deck of the Glomar. But because their eyes were trained on the Soviet submarine and the Cold War chessboard, they missed the miracle. Had a single scientist on board thought to place a voltmeter across the surface of a fresh nodule, or tossed a cluster of them into a sealed bucket of seawater with an oxygen sensor would have accelerated our understanding of deep sea and planetary biology by decades. We would have discovered dark oxygen half a century before Andrew Sweetman. We would have known that parts of the deep ocean can generate oxygen locally independent of sunlight. Instead, the samples were cataloged, analyzed for their metal content, and then largely forgotten in storage lockers. We spent the next 50 years debating the economic viability of deep-sea mining, viewing the CCZ solely as a resource map. We mapped the gold, but we missed the heartbeat. This is a classic case of observational blindness. Science finds what it is looking for. We were looking for metals to build tanks and later smartphones. We were not looking for a planetary life support system. This historical oversight forces a terrifying question upon us today. If we could miss such a fundamental mechanism here on Earth, on our own planet, in samples we physically touched, what are we missing? When we look at other worlds, we currently scan the heavens for Earth-like planets, blue marbles orbiting warm yellow stars, because that is our bias. We assume life needs a sun, but the nodules suggest that a rocky ocean floor can generate oxygen in total darkness, a prerequisite for aerobic ecosystems. This realization shifts our gaze from the distant stars back to our own solar system. We don't need to look at exoplanets light years away to find a dark ocean. We have them right here orbiting Jupiter and Saturn. And if the mechanism of the CCZ holds true, those frozen moons might not be the sleeping, suffocating tombs we thought they were. They might be breathing. If the geobattery hypothesis holds true for Earth, it does not stop at our atmosphere. Physics is universal. If saltwater rock and electrochemical potential can create oxygen here, they can create it anywhere. And this realization compels us to turn our gaze toward the outer solar system, specifically to the icy moons of Jupiter and Saturn. For decades, astrobiologists have looked at Europa and Enceladus with a mixture of hope and skepticism. We know they hide vast oceans beneath kilometers of ice. However, the prevailing dogma has always been that these oceans must be energy poor. Without sunlight penetrating that thick shell, photosynthesis is impossible. Therefore, we assumed any life there would be microbial, slow, and anaerobic, clinging to faint thermal vents, eking out a meager existence in the dark. We assumed they were starved worlds, but the discovery in the Clarion-Clipperton Zone shatters that assumption. Consider the architecture of Europa. It has a rocky mantle in direct contact with a saltwater ocean. It is subjected to immense tidal forces from Jupiter, which knead the moon's core like dough, generating heat and likely fracturing the seafloor, exposing fresh mineral surfaces. It is a perfect reactor for the dark oxygen mechanism. If the seafloor of Europa is paved with polymetallic nodules or similar geobattery structures formed by precipitating metals, then that alien ocean is not anoxic. It could be oxygenated, highly oxygenated. This changes the biological potential of the moon entirely. Oxygen is the high-octane fuel of metabolism. It allows for size, speed, and complexity. On Earth, the rise of oxygen triggered the Cambrian explosion, turning a world of slime into a world of predators, eyes, skeletons, and brains. If Europa has a planetary respiration system powered by its geology, it might host not just microbes, but macrofauna. Imagine blind bioluminescent leviathans hunting in the deep, powered by the breath of stones. But this gift of oxygen comes with a heavy price. It comes with a ceiling. The ice shell of Europa is estimated to be 15 to 25 kilometers thick. For any civilization arising in that deep ocean, this ice is not just a weather phenomenon. It is the boundary of the universe. We call this the stone sky scenario. An intelligent species evolving in such an environment would have no concept of stars, galaxies, or other worlds. Their cosmology would be defined by the world ocean below and the hard sky above. They would be protected from asteroids and cosmic radiation, safe within a cosmic womb. But they would also be prisoners. This brings us to the most chilling implication of the dark oxygen discovery. A new solution to the Fermi paradox. The Fermi paradox asks a simple question. If the universe is billions of years old and teeming with planets, where are the aliens? Why is the sky silent? The dark oxygen mechanism suggests a terrifying answer. It proposes that the universe isn't empty, it's just locked. Statistically, ocean worlds such as Europa or water-rich planets appear to be more common than surface worlds like Earth. Therefore, the statistical majority of life in the universe likely exists in dark subsurface oceans. If these worlds are oxygenated by geobatteries, they could easily produce intelligent tool-using civilizations. But here lies the metabolic trap, a systemic failure mode that prevents these civilizations from ever leaving their cradle. Let's run the simulation. Imagine a smart aquatic species on a Europa-like world. They develop language, culture, and basic tools using bone or stone. Eventually, like us, they desire to advance. They want to pierce the stone sky to see what lies beyond. To do that, they need technology. To build technology, they need metal. But in an ocean world, you cannot smelt metal. You cannot light a fire underwater. The only accessible source of dense, refined metals would be the nodules scattering their seafloor, the very stones that are generating their oxygen. This is the great filter. To build the machines necessary to breach the ice shell, they must harvest the nodules. But the nodules are their life support system. As they industrialize, they begin to strip mine the seafloor. They pull up the batteries to build the drill. The feedback loop is immediate and catastrophic. As mining scales up, the planet's electrochemical oxygen production plummets. Hypoxia or oxygen deprivation sets in. Dead zones expand. The food chain begins to collapse from the bottom up. It is a case of self-asphyxiation. The civilization literally suffocates itself in the pursuit of progress. They trigger a mass extinction event before they ever breach the ice. They die in the dark, surrounded by their half-finished machines, wondering why the air turned stale. This metabolic trap explains the silence of the universe. It suggests that most civilizations are aquatic, and they are rigorously filtered out by the physics of their own environment. They are trapped between a ceiling of ice and a floor of batteries. To touch the ceiling, they must destroy the floor. It is a tragic, elegant, and horrifying mechanism of cosmic selection. It filters out those who cannot balance their hunger for resources with the integrity of their life support system. And this is where the story stops being about aliens and starts being about us, because we are currently standing on the edge of the exact same trap. We are not trapped under ice, but we are trapped by our energy needs. We are looking at the Clarion-Clipperton Zone with the same hunger that the doomed Europans might have had. We see the batteries, we need the metal, and we are preparing the dredgers. The cosmic filter is not just a theory for distant moons. It is a test, and we are taking it right now. The discovery of dark oxygen forces us to confront the most difficult paradox of the 21st century, the green dilemma. We are currently racing to decarbonize our civilization. To save the atmosphere above, we are electrifying everything. We need billions of batteries for electric vehicles, wind turbines, and grid storage. This requires immense quantities of cobalt, nickel, and manganese. The Clarion-Clipperton Zone is estimated to contain metal resources comparable in scale to major terrestrial reserves. The narrative sold by deep-sea mining proponents like the Metals Company is compelling. They argue that harvesting nodules is the lesser evil. There are no rainforests to burn at the bottom of the sea, no indigenous villages to displace. They frame it as picking up rocks from a desert. But we now know it is not a desert. It is an active electrochemical environment. If we proceed with industrial-scale mining, we are not just removing mineral deposits. We are physically removing the electrodes of the planetary life support system. When a collector vehicle sucks up a nodule, it likely disrupts local electrochemical oxygen production for timescales far longer than any human planning horizon. This is the crucial distinction. A forest, if cut down, can regrow in a century. A manganese nodule takes 10 million years to grow a few millimeters. On human timescales, this damage is absolute. It is an irreversible ecological threshold. We are effectively flipping a switch from on to off across millions of square kilometers of the ocean floor. We do not yet know the load capacity of this system. How much of the abyssal grid can we dismantle before the global ocean chemistry shifts? How many dead zones can we create before the carbon sequestering power of the deep ocean collapses? We are acting like the hypothetical engineers of Europa, tearing apart our foundation to build a ladder. We are risking the stability of the biosphere to fuel the transition of the technosphere. The system investigator must conclude this inquiry with a warning. The anomaly of dark oxygen is not just a scientific curiosity, it is a boundary line. It teaches us that the Earth is far more complex, interconnected, and alien than we assumed. For 50 years, we looked at these black stones and saw only dollars in voltage. Now we must look at them and see breath. One possible explanation for the cosmic silence is that similar constraints may limit other civilizations. They chose the metal over the mechanism. They chose expansion over equilibrium. We still have a choice. The sensors are still running in the deep, recording the pulse of a living planet. The question is no longer, are we alone? The question is, are we capable of aligning technological progress with planetary stability? The ocean is breathing. We would do well to let it continue.